So now that we learned about vector operations, we can talk about properties of vector operations. So we're going to assume that we have three vectors, u, v, and w. These are all vectors. And c and d are going to be scalars, so they're just coefficients. They're not, or scalars, they're not vectors. And so a lot of these properties are going to be ones that you're familiar with from numbers. So the first one is if I add two vectors together, addition is commutative. So u plus v is the same thing as v plus u. Addition is associative, so if I add u and v together and then add w, it's the same thing as adding u to the sum of v and w. If I add the zero vector to a vector, it leaves it alone. So u plus 0 is u. If I add a vector and it's negative, you get the 0 vector. If I do a scalar multiple, c times another scalar multiple, it's the same thing as multiplying the two scalars together and then doing scalar multiplication. If I add two scalars together and then do scalar multiplication, it's the same thing as doing each individual scalar multiplication and then adding. Scalar multiplication distributes over addition. So this is the same thing as cu plus cv. And the final property is if I take and do the scalar multiple 1 to a vector, it leaves it alone. And if you do a scalar multiple by 0, you get the 0 vector. All right, so those are the properties of our vector operations. I do want to mention another property that we have. So the length of a scalar multiple, the length of c times the scalar multiple cv, it's the length of the vector v times the absolute value of c. So remember when I said scalar multiples are a way of stretching or shrinking? That's kind of what this statement is saying essentially. Is it either stretches out the vector or it shrinks the vector. All right, so now for the final topic, let's talk about unit vector in the direction of v. So sometimes we have a vector that's not a unit vector, but we kind of want to turn it into a unit vector. So how do we do that? If v is a non-zero vector, you have to start with a non-zero vector, then the vector u, which is going to be the vector v divided by the magnitude. Another way to think of this is really the scalar multiple 1 over the magnitude of v times the vector v. This vector has length 1. Remember what it means to have length 1. That means it's a unit vector and the same direction as the vector v. So what you've done is you've taken your vector v, you're still in the same direction as v, but all you've done is you've changed the length to make it a unit vector. So let's look at this example. Let's find a unit vector in the direction of the vector v, which is -2, 5, and verify that it has length 1. So I want to find a unit vector in the direction of v. So we need to find the vector u. Well, we have a nice formula for this vector, but I'm going to need the length of my vector v. So that's the first quantity we're going to find. Let's find the length of our vector v. Well, remember, we square our entries, add them together, and take the square root. So this is the square root of 29. That's the length of v. So to get our unit vector, I'm going to take 1 over the magnitude, which was the square root of 29, 1 over the square root of 29, and do the scalar multiplication with the vector v, -2, 5. So if I distribute, I'm going to get my unit vector Now the problem did want me to verify that this is a unit vector. So the way we verify it is by checking the length of this vector, and remember the length needs to be 1. So if I compute the length of this vector u, square root of this squared plus the second entry squared. So this will be the square root of 4 over 29 plus 25 over 29, which is the square root of 29 over 29, the square root of 1, which is 1. So this is, in fact, a unit vector, and it has the same direction as the vector v.